Bismillah ar-Rahman ar-Rahim. We are going to discuss today solubility, which is chapter 6 in Barber's book. First of all, we're going to talk about the concept of solubility. We had mentioned before what we mean by the saturated vapor pressure, and it is expressed downwards, as we can see from the figure. It will be seen now. You have a container. The container is full of liquid. Some of the liquid molecules enter the gaseous stage, and some of it return back to the liquid stage. So there is some going out and some going down. Of course, it's temperature dependent. There will come a time where the amount entering equals the amount of molecules leaving. At this point, we say that the vapor pressure on top of this liquid is saturated, fully saturated. There is always another gas present on the top of this liquid. Suppose this gas, we can consider it as nitrogen. Also, nitrogen enters this liquid phase and comes out from the liquid phase, and there will come a time where the amount entering equals the amount leaving. At this point, we say that we have a saturated solution of nitrogen. Now we come to the factors affecting solubility, which are four. The first of them is Henry's law. As we can see from the figure, we have two cylinders. The two cylinders are at a temperature of 20, which is the ambient temperature. And suppose one of the cylinders has a pressure of 100 kilopascal, يعني الضغط الجوي, and the other one is 200 kilopascal, which is twice the atmospheric pressure. This pressure is capable of driving more molecules on top of the liquid into the solution. As you can see below in the figure, there is as much more molecules of nitrogen entering the liquid phase, comparing with that on the left side where the pressure is only 100. We must go ahead till we find stabilization. That what we mean that we'll keep on waiting till we have a equilibrization. At this point, we can say that at equilibrium of the pressure, there is as much as amount of molecules of nitrogen in the stage where the pressure is 200 compared with that on 100. As you can see, there's only 3 molecules on the left compared with 6 on the right. So this is the first factor affecting the solubility, which is the partial pressure. Henry's law denotes this principle. So whenever we want to discuss Henry's law, we can say it in such a way. We must put in the constant at the first beginning. We say at a particular temperature, whatever the temperature, amount of given gas dissolved in a given liquid is directly proportional to the partial pressure of the gas in equilibrium with the liquid. So we must have equilibrium. We must wait till there is stability. What is the clinical application of such this statement? Is the deep sea divers, الغواصين اللي بينزلوا تحت المية, whenever they go downwards with the high pressure, definitely more nitrogen their body will dissolve in their liquids. So when they come abruptly, rapidly, the nitrogen, due to difference in concentration and pressure, comes out speedily, causing what we call bends or a deep sea driver, casein disease. This bubbles that occur can block joints, can affect pulmonary circulation, and can lead to bad sequels. This occurs also in people work in the hyperbaric chamber, الغرف اللي موجوده تحت الميه، الضغط الجوي بتاعها بيبقى الضعف، فطبعا دول لو خرجوا مره واحده طبعا they are liable to get what we call deep sea drivers. This is the first factor affecting the solubility, which is the partial pressure. The second one is the temperature. As you can see from the figure, we have two cylinders. One of the cylinders is subjected to temperature 20, and the other one is subjected to temperature 37. We have nitrogen, and we have nitrogen on top of the liquid. At this circumstances, at this difference in temperature, definitely, as we can see, that more nitrogen is being absorbed in the unit or in 1 liter of water, more than that in the circumstances where the temperature is 37. يعني عند 20 و 37 we can see that it is 0.016 and 0.014. Most probably you must memorize these figures, because whenever you want to express yourself as an example in exam, you must put this figure in your mind and try to memorize it. You have 6.16 and 0.14. This at the temperature of 37. So this is the second factor. Whenever the temperature is high, less capability for the gas to be soluble in the liquid. What is the relevant of it in our work? The kettle, whenever the kettle begins to boil, we find this smear occurring. What's the meaning of that? That this smear means that the bubbles are being expelled from the liquid. This why? Because of course, as we said, the more the temperature is increased, the less gas is being dissolved. The second thing is the heating coils that the warming heating coils that we put on the suppose on the blood bags to heat the blood. In such cases, if the blood is high, we can find bubbling coming out of this solutions, which is blood, and it may affect the patient. The third factor affecting solubility, as we can see from the figure, we have two cylinders. One of this we put in nitrogen exposed on the liquid, and the other one, the liquid is being subjected to nitrous oxide. The temperature is 37, which is the normal human temperature. We can see that there is less absorption of gas in the liquid as regarding nitrous oxide in comparison to nitrogen. You can see the 0.014 that we had mentioned before. So this is easy to memorize, compared with the 0.39 of nitrous oxide being absorbed in temperature 37. So we can see that nitrous oxide definitely is less absorbable than nitrogen in 1 liter of water. So this is the third factor affecting solubility. The last factor, of course, is the type of liquid. We can see from the figure that we have also two cylinders and the temperature 37. And we have, as we mentioned before, repeated from the previous example, we have the nitrous oxide, the figure 0.39 liter of nitrous oxide being absorbed in such circumstances. On the other hand, in a liter of water, on the other hand, if we replace water with blood, we can see that the absorption is only 0.5 0.47, which is a figure we must memorize. This is what we call the blood gas partition coefficient of nitrous oxide. So that definitely nitrous oxide is less absorbed in blood in comparison to water. So these are the 4 factors. To summarize, the 4 factors affecting the solubility of gas in a liquid. Okay. Now we come to what we call solubility coefficient, معامل الذوبان. Of course, when we have a solid, whenever we dissolve a solid in a liquid, we say that there is the amount of solid in this liquid is expressed as millimoles or moles. But whenever I use a gas to be dissolved in liquid, we use volume. Whenever we discuss any gas, we must put in our point from the scientific point of view that we must use what we call the standard temperature and pressure. This means يعني لازم نرجع حالة الغاز للحالة اللي هي ستاندرد، اللي هو حالته في الحرارة الصفر وحرارة والضغط الجوي 1 atmosphere. This is the standard that most scientific researchers use, is to refer or to regain the situation of the gas in such circumstances where the pressure is 1 atmosphere and the temperature is 0 degrees Celsius or 273 Kelvin degree. The first coefficient is what we call the Bunsen solubility coefficient. The Bunsen or معامل. معامل, what's the meaning of معامل? I want to see, in other words, how amount of the gas is being distributed between the blood and the gas, the blood and water. You see, I'm sorry, between a gas and a liquid, So whenever I want to define this coefficient, we begin to say it is the volume, like Avogadro's hypothesis, the volume of a gas, But this volume of gas must be corrected to standard temperature and pressure. What's the meaning of that? At a particular temperature, each gas definitely has a special volume and a pressure. No, at this particular temperature, I want to regain the gas. بجيب الغاز عايز ارجعه لحجمه لما يكون الحرارة صفر والاتموسفيريك بريشر. وفي الظروف دي اشوف قد ايه how much of this gas is being dissolved in the unit volume of a liquid. Unit volume of the liquid at the temperature concerned, whether the temperature is 30, 40, 40, 30, whatever. But the point is that I must regain the situation of the gas in the standard temperature pressure. ارجع اشوف وضعه شكله عامل ازاي في هذه الظروف. You see, you must regain the situation of the gas in the standard temperature pressure. And at that point, I see how much of it is being dissolved. So I want to compare the volume dissolved to the volume that which is not dissolved. So we will gain a figure. We call it a blood gas, suppose a blood gas partition coefficient. But this point is only used, or this coefficient only used by scientists, researchers. You see, in anesthesia, we use what we call the Bunsen coefficient instead of the Bunsen. We use Oswald solubility coefficient instead of the Bunsen. At this point, we just want to know how much of this volume of gas is being dissolved in a unit volume of liquid. I don't have to regain this volume to the standard situation and pressure. يعني ايه؟ يعني انا عندي غاز، اشوف قد ايه من هذا الغاز يذاب في وحدة الحجم. مش مهم الغاز اللي انا عايز اعرف قد ايه داب، ارجعه للستاندرد تمبشر بريشر. عكس البونسن. I I must know, or I want to put this gas to its standard situation. But in what we call the Oswald solubility coefficient, I don't have to return the gas to the situation where it is standard. So we say at a particular temperature, the volume of the gas, dissolve it in unit volume of liquid. Nothing to do more than that. I don't have to correct. مش لازم أصلح الوضع علشان يبقى الغاز يبقى في حالته اللي هو درجة حرارة temperature is 1 is 0 I'm sorry أو 273 273 Kelvin and the pressure of 1 atmospheric pressure. No, I don't have to do that. I want to know how much of it is being dissolved. You see? And we can, after that, we can get a figure. So the Oswald is the volume of a gas, dissolve it in unit volume of liquid at the temperature concerned, whether it's 30, 20, 50, whatever. But on the other hand, the gas which is dissolved, I don't have to, مش لازم ارجعه لحالته اللي هو الستاندرد temperature pressure. خلاص؟ Another point that the Oswald partition coefficient, the Oswald coefficient of solubility is not affected much by pressure. It's not affected by pressure. And we can see from the figure what's the meaning of that. What's the meaning of that? What's the meaning that the Bunsen, the Oswald solubility coefficient is not affected by pressure? Suppose we have two cylinders. One of the cylinders is under pressure of 100 and the other one is under the pressure of 200 and the temperature is 20, which is the ambient temperature. You can see as regarding Henry's law differently that there are more particles being dissolved on the right side instead of in comparison to the left side, definitely because we are using Henry's law. We are using Henry's law. Okay, well and good. Okay, now we have more molecules. We have more molecules. But if we apply Boyle's law, we can say that the more molecules on the right side, where the pressure is more, according to Boyle's law, will have a low volume. In comparison to the left one, we have the molecules are on normal pressure to the volume. Will be not much affected like the right one. In other words, أو في طريقة معينة إن الضغط مش هيأثر على الحجم مش عدد الموليكيولز on the volume, not the number of molecules. It will not be affected by the volume. It will affect differently the number of molecules dissolved. The end result, I want to say that the pressure is not affecting the volume absorbed, because though the number of molecules, عدد الموليكيولز أكتر، ولكن هم نتيجة للبويلز لو في حجم أقل، وهذا الحجم يواكب الرايت سايد يواكب الليفت سايد، وبالتالي ال two different pressure will yield the same volume absorbed, though there are more molecules on the right side in comparison to the left side. But if we use Boyle's law, we can some sort of correct this concept, putting in our mind that الضغط لن يؤثر على الناتج النهائي للحجم الفوليوم absorbed, not the amount. You must put in your mind the difference between the amount and the volume. The concept of partition coefficient is similar to Oswald partition coefficient, but there are two main differences or three main differences. First of all, that we can see they are almost similar to each other, but the difference is when we use Oswald partition coefficient, we always say blood gas. يعني the blood in comparison to gas, nitrous oxide is 0.47. You see, we must put them in what we call order. We must put them in the order. This is the first thing. What is the statement of the partition coefficient? Partition coefficient is similar to that of Oswald, but we say the amount of substance present in one phase compared to the another. The two phases differently are equal in volume and in equilibrium. يعني لازم التو فوليومز يبقوا زي بعض ويحصل نوع من التعادل في الضغط. يعني نقعد نستنى لحد ما الضغط اللي فوق يساوي الضغط اللي تحت. خلاص؟ يعني نجيب لتر على لتر وضغط هنا يساوي الضغط هنا. يفضل الغاز عمال داخل جوه الليكويد لحد ما يحصل stabilization، لحد ما يقف الوضع. at this point هبص تلاقي الضغط اللي في الحاله الغازيه يساوي الضغط في الحاله اللي مش غازيه اللي هو مذاب. خلاص؟ دي at this point بشوف قد ايه هنا بالنسبه لهنا. البارتيشن كوفيشنت لازم اقول الاوردر، انما يعني قصدي اقول البلاد جاز ممكن يبقى جاز بلاد وهناك فرق. انما الاوزوالد انا بقول البلاد جاز. انما البارتيشن كوفيشن اول ديفرنس ان ممكن اغير الاوردر. يعني بمعنى البلاد جاز بارتيشن كوفيشن اوف نيتروس اوكسايد is 0.47. Suppose we use what we call a gas blood partition coefficient, it will yield a figure of 2.1. That this is the first difference between partition coefficient and Oswald solubility coefficient. The second thing is that I can use two liquids. I can use oil and blood. We know nitrous oxide absorption in the blood is 0.47 liter. If we use oil, we always use oil in our testing instead of fat because it's more practical. So oil is like fat. You want to study fat, use oil. So the difference, the second difference is that we can use two liquids, but in the Oswald only we use blood gas. We use a gas and a liquid. So in the difference between the absorption of nitrous oxide, difference between absorption of it in blood and in liquid is in oil is 1.4 more in oil. In blood is only 0.47. So this is the second difference between the Oswald and the partition coefficient. The word tension, whenever I say the gas tension is the partial pressure, the partial pressure of the gas in liquid. But the partial pressure is the pressure of the gas in a gas state, not any liquid. So دايما لما نقول ضغط الغاز جوه البلد نقول الاوكسجين تنشن، انما ضغط الجوز في الجو بنقول عليها البارتيشن coefficient. البارشال بريشر التنشن طبعا we mentioned before in physics was the meaning of tension to the force of the force, as we mentioned before. This is a diagram showing the partition coefficient of the blood gas partition coefficient of nitrous oxide. Different is 0.47 in comparison to ether, which is I think 12 point some. So these three reservoirs showing the inspired anesthetic concentration both types, and then the inspired concentration in the lungs, and then in the tissue. We can see because the nitrous ether is more dissolved in blood, it's been taken too much from the blood to go to the tissue. Whenever it reaches the tissue, in a less tension than that of nitrous oxide. Why? Because it's been taken much from the alveoli or from the lungs. That means that I can develop a tension, a proper tension of nitrous oxide in the alveoli more than ether. يعني النيتروس اوكسيد بيتاخد بشويش من الدم عكس الايثر بيتاخد ببطء، وبالتالي يبقى النيتروس اوكسيد in the alveoli is more is easy to be increased in comparison to that of ether, so that we can have a much nitrous oxide tension in the alveoli compared with that of ether. And can we see that the channels of the ventilation and the perfusion cardiac output there is a difference, showing that there is much ether being taken from the lungs to the tissue regarding ether. You see, this is why ether has a slow induction and a slow recovery, because the affection of anesthetics on the brain depends upon tension more than a concentration. So whenever you have a developed tension in the alveoli, لما تكتر الضغط الغازات في الالفيولاي it's mirrored، يعني بيبقى مرايه للي موجود في البرين. فالايثر ضغط the tension of ether in the alveoli differently, because it's been taken much than ether, it will develop slowly, and so that the tension in the brain will be less. This is why nitrous oxide has a rapid onset and a rapid offset of anesthesia. We have a curve showing what we call build-up exponentials. We said before what's the meaning of exponential, which is non-linear. يعني الكيرف is not going straight forwards. That it is bended. It has a slope. We will not go through all the what's the meaning of exponential more than that. So this figure shows the build-up exponential of nitrous oxide and ether. What's the meaning of that? Whenever I apply the anesthetics to the patient, we can see, because the blood gas solubility coefficient of nitrous oxide in comparison to ether is very less. This is why within 10 to 20 minutes we have 100% of nitrous oxide build inside the alveoli after 10 to 20 minutes. But for ether, we have a much less concentration. Why? Because ether is being taken much from the blood via the cardiac output, so that there is not much ether being tension of ether being developed in the alveoli. This is what we call the exponential curves as regarding anesthetics, inhalation anesthetics. Putting in our mind that within a brief period, we find that the inhalation anesthetic ether reaches 100 within 10 to 20 minutes. We have two concepts. We have what we call the diffusion hypoxia and what we call the second gas effect. Whenever we have amount of gases, mixture of gases, these gases affect the partial, the net result of their concentration and pressure in the mixture. In other words, we have the Benedict cross, as we mentioned before. We have the gases being forced to the bill by the expiration of the patient. The gases, suppose it has nitrous oxide and oxygen and nitrogen. Nitrogen is more soluble, or I'm sorry, nitrous oxide will be more soluble than oxygen or nitrogen. So it will be taken from the mixture of the gases expired the patient more than the others, so that the other gases develop a more concentration than before the nitric oxide. يعني معنى لما النيتروس اوكسيد اتاخد هيبقى على حساب الغازات الثانيه تزيد، فده السكند جاز افكت. يعني النيتروس اوكسيد affected the concentration of the other gases. We have also this in nitrous oxide and hallucine anesthesia. Suppose what's the meaning of the nitrous oxide can affect hallucine? In other words, if nitrous oxide is being taken from the mixture of the gases in the alveoli, we can see that the hallucine concentration will increase. The tension of it will increase, so it will hasten the effect of hallucine. يعني الغاز اللي اتاخد هيخلي الغاز اللي لسه ما اتاخدش ضغطه يزيد وبالتالي تأثيره يبقى أكتر. This is what we call second gas effect. On the other hand, we have what we call diffusion hypoxia. Whenever the patient is being in the recovered situation and I close suddenly the nitrous, difference of the tension of nitric oxide in the patient in the atmosphere makes the nitric oxide go speedy. Nitric oxide يخرج بسرعة جدا. Taken with it carbon dioxide, impairing oxygenation. You see, this is what we call, if we close the nitrous oxide before oxygen, we can see that the patient can develop hypoxemia and hypocapnia. Why hypoxemia? Because the nitrous oxide will fill the alveoli, impairing oxygenation. At the same time, because of its speed excursion, it will take more carbon dioxide. This is what we call diffusion hypoxia. The last thing is this. You can see the difference between the three anesthetics as regard dissolving in the oil. We can see that as we mentioned before, the nitrous oxide is 1.4. The difference, the partition coefficient, and regarding hallucine is 224, which is more soluble in oil. This denotes the potency of the anesthetic, not the blood gas partition coefficient. There is a difference. You have a potent, but you have a less anesthetic regarding its onset and offset. This curve shows the anesthetics almost in a straight line, and the straight line has a slope. It's been spread all over the line. It's not on the line, upwards, downwards, all over the line. You see, this curve represents the MAC on one side and the solubility coefficient on the other side. If you have a high MAC, you have a less solubility coefficient, and vice versa. This is after what we call the Mayer-Overton theory. Which depends upon that anesthetics work by their solubility in oil or in fat. The theory depends upon this point. The last point is the solubility of anesthetics in fatty large chain fatty acids can affect the lines, the tubing system we use. Whenever isoflurane or suppose is being absorbed, it can affect the physical properties of these solutions because there is a solubility. Second thing, the reserve of isoflurane or whatever inhalation anesthetic use, it can be a reservoir for triggering what we call malignant hyperpyrexia. لعيانين معينين لما يتعرضوا للنيتروس اوكسيد للانهاليشن اسيتيك بيوتساكسينايد بيولدوا very high temperature and they can pass if we don't have what we call a dantrolene sodium. This also is the theory of what we call the how anesthetics works by changing the configuration of the fatty acid, long fatty acid, and similar change of the receptors. So it will close the receptor up or open the receptor according to their absorption on this fatty acid change. This is, of course, is reversible, regaining the van der Waals bounds off between the molecules. I hope that I did my best. I hope I succeeded to an extent. I will improve myself different day by day. اللي عايز اقوله ما تنسوش الكوفيشن. مشكله الكوفيشن الناس مش فاهمها. الكوفيشن عباره عن يعني ايه بونسن ويعني ايه الاوزود. البونسن هو عباره عن ذوبان الغاز في الليكويد، والتاني برضو ذوبان الغاز في الليكويد. انما البونسن لازم الغاز اللي هيدوب لازم ارجع حجمه للاساسيات. يعني لازم اشوف الحجم لما تكون الحراره صفر والضغط 1 اتموسفير، واشوف بعد كده قد ايه منه هيذوب at a particular temperature. ولكن الاوزود لا، الاوزود انا باخد حجم الغاز 3 لتر 2 لتر مش كذا لتر، واشوف قد ايه منه هيداب. ال 3 لتر داب منه 2 لتر، يبقى النسبه 3 ل 2. انما البونسن انا الغاز ده مش 3 هشوف قد ايه يدوب 2، لا لازم ال3 ارجعه لحالته بحالته قد ايه الفوليوم بتاعه لما الحراره تبقى صفر والبريشر بقى 1 اتموسفير. ده this is the difference. خلاص، والسلام عليكم ورحمه الله وبركاته.